Assalamualaikum warahmatullahi wabarakatuh. So before I start, I will introduce myself first. So my name is Najla Anira Putri, with the last digit of my number student is double one and two. And in this occasion, I will talking about exploring bioplastic through the lens of aerobic and anaerobic biodegradation. And this presentation I made for um chemi- chemical physics class with Dr. Heri Satya Kusuma, SSI MTech. So let's get started to the discussion. So before we get into the main discussion that bioplastic and biodegradation, we will talking about the plastic first. So the plastic itself play an important role as a result of their many applications, such as packaging, building materials, and commodity, as well as hygienic products. However, because of their persistence in the environment, the increased cost of solid waste disposal due to the reduction in available landfill space, as well as the potential hazard from waste incineration, polymers become a waste deposit problem. Thus, biodegradable polymers as a potential partial solution of these problems were developed during the last decade. So one of the solution of the plastic itself is bioplastic. So bioplastic, owing to their biodegradability and circularity potential, the use of biodegradable bioplastic or BBS has gained increasing momentum due to the global plastic pollution problem. According to European Bioplastic 2021, although the BBS produced worldwide amount 1.2 million tons in 2020, currently represent a small share around 1% of the global production of plastic. A significant market growth for BBS of almost 50% is expected by 2025. Biodegradable plastic are designed to degrade under environmental conditions or in municipal and industrial biological waste treatment facilities. Aerobic composting as well as anaerobic biogasification of waste are currently in use. The latter process becoming more and more established because of the added benefit of energy conservation due to biogas recovery. So we come to the classification of plastic. Plastic is divided become two types. That is thermoplastic and thermosetting plastic, or we call it thermosets. Thermoplastic and thermosetting plastic, or thermosets, are the two primary types of plastic. Thermoplastic materials have the ability to be repeatedly melted, reshaped, or recycled, and soft, as an example in injection molding or extrusion resins. On the other hand, products made from thermoset material do not have the same characteristic. The term homopolymer is used when the polymer in the plastic is derived from a single monomer. Conversely, the term copolymer is used to describe a polymer this is derived from two or more monomers. Thermoplastic materials can be further categorized into two main groups: amorphous and semicrystalline. Amorphous thermoplastic, like polystyrene, are typically stable, clear, rigid materials with little shrinkage and no specific molecular structure. In contrast, crystalline polymer exhibit both amorphous and a systemized crystal-like structure and are commonly known as semi-crystalline thermoplastic. Compared to the amorphous thermoplastic, semi-crystalline polymers tend to be more durable and less brittle. They often have higher heat desorption temperatures as well. Semi-crystalline thermoplastic have a higher specific heat, greater shrinkage, and can be translucent or opaque. One well-known semi-crystalline thermoplastic is polyethylene. So we come to the classification of bioplastic. So the popular one is PLA or polylactic acid. So what is polylactic acid is PLA or polylactic acid is one of the most well-known forms of bioplastic. Global production of PLA reached approximately 190,000 tons in 2019. When compared to the majority of the other biodegradable polymers, PLA showcase superior mechanical strength, durability, and transparency. Its application is widespread, particularly in milk packaging and single-use items. Given ideal condition, PLA can be completely decomposed by bacteria within a few months, resulting the production of biomass and gas. This natural breakdown process makes PLA compostable, contributing to environmentally friendly nature. To initiate the self-hydrolysis process that breaks down the PLA polymer into lactic acid, specific conditions to moisture and temperatures exceeding 140 degrees Fahrenheit are required. In the absence of this condition, PLA cannot decompose effectively. Additionally, as PLA composes, it releases acid, leading to an increased acidity in the composting environment. Instead of compositing PLA, an alternative approach is to recycle it. However, it is essential to ensure proper recycling practices, including appropriate sorting and processing. By carefully recycling PLA and using it multiple times instead of using it as a single-use item, we can minimize its environmental impact and promote sustainability. So the next one is bioplastic derived from plants. The bioplastic made from raw wood starch have the advantage of greater extendability compared to the other bioplastic before reaching their breaking point. The ranking of 6 bioplastic from weakest to strongest is as follows. The first one, rice flour, potato flour, tapioca starch, corn flour, and arrowroot starch. Among them, arrowroot starch-based bioplastic stands out as the strongest and most flexible, capable of bending without breaking. Starch-based bioplastic, particularly those made from finer-grained powders, tend to be stronger due to their tightly packed molecules. The physical characteristic of bioplastic products, such as flexibility and thermal resistance, can be modified by altering the polymer backbone, creating blends, or adding other molecules such as plasticizers. For example, it phthalates into the polymer. There is a table that shows melting and glass transition temperatures of prevalent bioplastic. There are two temperatures. The first one is melting temperature, and the second one is glass transition temperatures. And there are a view of bioplastic, that is bioplastic, composite bioplastic, PET, PHA, PLA, PBS, and PTT. The first one is TM. TM is the point at which materials change from a solid to a liquid. So the highest melting temperature is, we can see here, composite bioplastic, and the lowest one is PET. And then the next one, there is glass transition temperature, which is the temperature at which an amorphous polymer changes from a hard or glassy state to a soft, leathery state, or vice versa. We can see in the table that the highest glass transition temperature is PET, and the lowest one is PBS. And then in the depolymerization of commercial plastic, achieving thermal stability in plastic degrading enzymes is critical, especially for plastic with high glass transition temperatures. Next to biodegradation, the aerobic biodegradation behavior of plastic is well studied, and many polymer degrading microorganisms have been isolated and identified. The evaluation of the anaerobic breakdown of plastic, however, is still in a developing stage, and only few reliable investigations are available. The complete mineralization to methane and carbon dioxide of the polymer under anaerobic condition involve successions of syntropic association. Hence, most anaerobic biodegradation studies of polyester have focused on mixed and unspecified population, such as diverse anaerobic sludges and sediments. Investigation using individual cultures were restricted to the degradation of polyhydroxybutyrate or PHB by a gram-negative obligate anaerobic bacterium Heliobacter delafield and the anaerobic biodegradability tests with divine cultures for other plastic are still missing. Despite of the extent and rate of biodegradation of several bioplastics have been previously investigated in different environments under both aerobic and anaerobic conditions. The results obtained are not conclusive, and more studies are needed to deepen our understanding of PBS biodegradation. We move to biodegradation utilizing microorganism. So um, biodegradation itself is defined as the mineralization of organic material by microorganism like fungi, archaea, and bacteria which eventually result in the final products carbon dioxide and water under the aerobic circumstances. When mineralization is not complete, biotransformation occurs, whether organic and inorganic metabolites or transformation products. The most important biodegradation processes for biopolymers, such as the hydrolysis of ester bonds to liberate the monomer, are executed by extracellular enzymes that are excreted by microorganisms. Biodegradation to small molecules need to occur outside of the microorganism because the substrate, the biopolymer that needs to be degraded, is often too large to be taken up. This active site of the extracellular enzyme forms a complex with the substrate and cleaves a part of it off. This smaller soluble part can be transported into the microorganism, and within the organism, compounds are further digested through endoenzyme. Most microenzymes use multiple enzymes to fully biodegrade a substrate. These enzymes are together called a system. Biodegradation of bioplastic in aerobic and anaerobic environments utilizing bacteria and fungi is a typical bioremediation approach. Bioplastic degradation enzymes typically belong to the proteinase, kinase, or esterase families. This enzyme often exhibit a degree of promiscuity which allows them to degrade bioplastic that are not their natural substrate. However, due to their large size, large polymers cannot be transported into cells and must first be broken down into smaller monomers and polymers. As a result, bioplastic degrading enzymes are usually secreted in such scenarios. Despite the many advantages of microbial enzymes in degrading bioplastic, challenges such as immobilization, activity, and stabilization under various conditions, as well as exposure to different types of bioplastic, pose hurdles in their practical use. And microorganisms play a vital role in modifying environmental substances through metabolic or enzymatic actions. Degradable bioplastic undergo a breakdown into carbon dioxide, methane, and microbial biomass via microbial activity. Carbon-based polymers serve as a carbon source for microorganisms, facilitating energy production. Microbial biodegradation begins with the assimilation of the polymer substrate by microorganism, followed by colonization. Subsequently, microorganisms enzymatically degrade the polymer into low molecular weight compounds before converting them into carbon dioxide and water. Bioplastic degradation can occur aerobically or anaerobically, which aerobic biodegradation yielding water, carbon dioxide, and microbial biomass as end products. Oxygen molecules act as electron acceptors in this process, facilitating the breakdown of bioplastic through four stages that are those are biodeterioration, biofragmentation, bioassimilation, and mineralization. In aerobic conditions, the majority of carbon from metabolized substrate is converted to carbon dioxide, releasing energy. However, the biological degradation process differs when microbial agents engage in physical action such as gnawing or boring. This physical uptake occurs at the structural level rather than at the molecular level of the polymer. Microbes exert mechanical, chemical, or enzymatic activities to facilitate degradation, which microbial species hierarchy promoting the increased biodegradation efficiency. Extracellular polymers produced by bacteria act as surfactants, expediting microbial access to surfaces. Biotic and abiotic factors depend on the specific experimental condition as well as the nature of the microorganism involved. Hence, more systematic comparative testing and mechanistic data on the biodegradation of BBS or biodegradation bioplastic is still needed to engineer biodegradable materials or products. To develop end-of-life management processes, and to gain a detailed and comprehensive understanding of the mechanism underlying bioplastic biodegradation. In this context, each biodegradation bioplastic or BPS material must be evaluated under the same testing scheme in order to achieve unbiased comparison of biodegradability results. The biodegradation extent of bioplastic is typically followed by measuring the oxygen demand or carbon dioxide evaluation, or the amount of carbon dioxide and methane uh, evolved in the plastic material is either aerobically or anaerobically biodegraded. Those biodegradation standard tests only account for the mineralized carbon, overlooking the carbon fixed in the form of cell biomass. The terms of mineralization and biodegradation are commonly used in interchangeably, interchangeably, interchangeably in the literature for the sake of simplicity. However, they are related to different processes. Um, However, mineralization is the last stage after biodegradation and biofragmentation, but is actually an important step in the biodegradation process. Mineralization provides information on the actual metabolic ability of a microorganism or community to convert monomers or polymers fragments, which have been generated in the previous two stages into biomass gases, carbon dioxide and methane, or carbon dioxide or methane, water, and potentially other metabolites. So we move to anaerobic biodegradation factors. Anaerobic biodegradability of bioplastic depends upon the type of bioplastic and on the operating condition of the process, such as temperature, hydraulic retention time or HRT, total solid content, and the temperature represents the main factor regulating the degradation of bioplastic. Since thermophilic temperatures are necessary to reach the glass transition of many bioplastics and allow the transition from their crystalline structure to the more degradable amorphous one. Even though some bioplastics are certified as compostable and degradable in anaerobic environment, anaerobic biodegradation of bioplastic is found to be only partial in real processes operated on a large scale and under real operating conditions. This fact limits bioplastic valorization through the biogas production and favors the permanence of bioplastic residues in the digestate. The latter factor may lead to technical difficulties in editing, plugging the pipes and pumps, and also impede the use of digestate in the agriculture. Bioplastic residues in Europe are currently not distinguished from other plastic residues under the legislation on organic fertilizers. So there are this is the mechanism of biodegradation of bioplastic, that this biodegradation is produced carbon dioxide, methane, water, and metabolites. And there are also some factors that affect the biodegradation. Several factors influence the rate of degradation, such as properties of polymer, including surface morphology, shape, crystallinity, including and side chain length of polymers, as well as the characteristic of degradation environment, including UV exposure, temperature, mechanical forces, nutrient levels, type of bacteria, oxygen level, and pH. So, this is the explanation of the picture before about the biodegradation mechanism. Biodegradation or biochemical degradation mechanism of plastic involve several steps. According to Deshan et al., the first step to achieve the biodegradability of plastic is breaking down of polymer chains by microorganisms to increase their molecular weight, where microorganisms defecate the extracellular enzyme depolymerizing the external cell walls and of the polymers. After that, the plastic materials get degraded by aerobic or anaerobic degradation. It is recommended that the degradation process takes place in 3 stages: biofilm formation or RB, depolymerization or RD, and mineralization or RM, or bioassimilation. The rate of RB is monitored via physical methods. The rate of RD is measured in situ, and respirometry method assesses the rate of RM under controlled laboratory conditions. An initial biodegradation process is RB, also known as biodeterioration, a complex association produced from a surface embedded microbial cells surrounded by soft-matte extracellular shell of polymeric substances, for example, like proteins, polysaccharide, and integrated inorganic or organic particles. A lagging phase, ranging up from days to weeks, is mostly monitored before the steady-state biodegradation is completed because it requires extensive duration to form biofilms and adjust its microbial population. The second step of biodegradation of bioplastic is hydrolytic depolymerization or enzyme catalyzed, which occurs when extracellular depolymerase catalyzes the cleavage of hydrolytic bond of polymers, forming monomers, dimers, and oligomers. The third step of biodegradation of bioplastic is mineralization or bioassimilation, from where small molecule uptake is ensured by cause during bioassimilation for reproduction, growth, and mineralization, which is collected into a single parameter. So, this is there is a picture that shows biodegradation of bioplastic in ecosystem that divided into two condition, that aerobic condition and anaerobic degradation that helped by microorganism. So the aerobic degradation under the presence of oxygen or aerobic condition, microorganism break down bioplastic, and the primary end products of this process are carbon dioxide and water. Meanwhile, the anaerobic degradation in environmental lacking oxygen or anaerobic condition, such as deep soil layers or submerged area, microorganism degrade bioplastic through anaerobic respiration. And then the final products include biomass, anorganic material used for microbial growth, and the energy for release in the form of biogas, that including methane. So, in research that they are doing aerobic biodegradation task and compare with the anaerobic biodegradation task. So this is the aerobic biodegradation task. The polymer biodegradation under aqueous aerobic condition was determined according to the standard ISO 14852, that determination of the ultimate aerobic biodegradability of plastic materials in an aqueous medium. A method by analysis of evolved carbon dioxide. In brief, the biodegradability test was carried out in 2.1 liter gas tight glass bioreactors. 1 liter of working volume containing either 150 milligrams per liters of the tested biodegradation bioplastics, or PBS, cellulose as positive control, or HDPE as negative control. 64.8 milliliter of the activated sludge inoculum, corresponding to a final concentration of 0.5 grams total solid TS per liters, and 935.2 milliliter of mineral salt medium freshly prepared with the following composition in milligrams per liter. That is potassium dihydrogen phosphate, AD5.0, the potassium hydrogen phosphate for 217.5, and then the sodium hydrogen phosphate dihydrate for 334.0, and then there is ammonium chloride 5.0, and magnesium sulfate heptahydrate 22.5, and calcium chloride dihydrate 36.4, and then ferric chloride hexahydrate 0.25. All chemical used were of analytic grade. Blank tests without any carbon source addition were also performed in parallel to correct for the background endogenous carbon dioxide production. The bioreactors were closed with bubble septa and aluminum caps, and incubated under gentle agitation at 4.5 rpm in a roller shaker placed in a controlled temperature room, 25 plus minus 1 degree Celsius, under diffuse light conditions. Activated sludge kindly supplied by the sewage treatment plant of Valladolid was employed as inoculum within 1 day after collection. This inoculum was not previously adapted to the biodegradation of the target plastic as the only carbon and energy source. The initial pH of the cultivation broth in the bioreactors was 7 plus minus 0.1. The carbon dioxide and the oxygen concentration in the headscape was measured periodically until the mineralization curve plated. When the oxygen concentration in the headscape decreased below 5%, the headscape was irradiated with an air compressor for 5 minutes to prevent oxygen limitation during the biodegradability test. All tests were performed in Triplicate. So for the another test, that anaerobic biodegradation test, polymer biodegradation under anaerobic condition was determined according to the standard ISO 14853, the plastic determination of the ultimate anaerobic biodegradation of plastic material in an aqueous system. Method by measurement of biogas production, the biodegradability test was performed in 2.5-liter gas-tight glass bioreactors using the same agitation apparatus and conditions. First, an aliquot of anaerobic inoculum was added to obtain the desired concentration of 1 gram total solid per liters, then 150 milligrams per liters of the test materials. Cellulose, or HDPE, was introduced accordingly, and finally the bioreactors were filled up with a divine mineral salt medium up to a total volume of 1 liter. The initial pH was 7.1. The bioreactors were then flushed with the pure helium gas for 5 minutes to ensure anaerobic conditions, which were corroborated by gas chromatographic analysis and the lack of color of resin, a redox indicator. An cubated the dirt under mesophilic condition, 36 plus minus 1 degree Celsius. And then for the mineral salt medium consisted of the following gram per liters. That is potassium dihydrogen phosphate 0.27, and then disodium hydrogen phosphate dodecahydride for 1.12, and then ammonium chloride 0.53, calcium chloride dihydrate 0.075, and then magnesium chloride hexahydrate 0.1, and then ferrous chloride tetrahydrate 0.02, and then azurin for 0.001, and then for sodium sulfite nanohydrate is 0.1. All reagents were of analytical grade. The methanogenic inoculum urine used was obtained from the mesophilic anaerobic sludge digester of Valladolid sewage treatment plant. This inoculum was obtained from the bioplastic anaerobic sludge digester. This inoculum was not acclimated for plastic biodegradation and was pre-incubated for 7 days at 36 plus minus 1 degree Celsius without addition of any nutrient and carbon source. In order to reduce the background gas production, prior to use, the inoculum was washed twice, mineral salt medium for 10,000 rpm for 10 minutes at 4 degrees Celsius, and suspended in fresh mineral salt medium to reduce its organic carbon contents less than 20 milligrams per liters. In the final test suspension, blank inoculum and mineral salt medium positive that play with cellulose and negative is HDPE control. Tests were also performed. All SI were conducted in a triplicate after 1 hour of incubation at 336 plus minus 1 degree Celsius. Gas pressure in the headscape was measured with a manometer, and the excess gas was vented in order to reach equilibrium. This pressure and concentration of carbon dioxide and methane in the bioreactor headscape were measured weekly until the mineralization curve plotted. So we come to the biodegradability rate. So what is biodegradability rate? The rate of biodegradability of bioplastic is evaluated by estimation of so-called biodegradability indexes, where these biodegradability indexes are related to composition and characteristics of bioplastic, such as surface morphology, molecular weight, and molecular weight distribution, and microorganisms activity. This is estimated by evaluation of carbon dioxide, oxygen, and methane, or oxygen or methane, which shows the main indexes of aerobic and anaerobic biological processes, respectively. Generally, conversion of carbon present in bioplastic to the carbon dioxide and methane, or carbon dioxide or methane, is widely used to test method to evaluate the biodegradability under anaerobic condition. The oxygen consumption or the carbon dioxide production are biodegradability indexes for aerobic environment, and biochemical methane potential is widely used method to stimulate anaerobic condition in the lab scale experiments. Other methods of evaluating the biodegradability reported in the previous literature are decrease in total carbon of bioplastic, visual assessment of surface erosion, or the discoloration assessment of oxo-degradable products, and spectroscopic spectra. Weight loss is also considered as biodegradability indicator or in the biodegradability index, despite the fact that mass loss can take place due to abiotic processes without involvement of microorganisms. So this is for the kinetic analysis. The anaerobic degradation performance of the substrate were gathered by fitting the cumulative methane yield curve with the Gompertz theoretical model, commonly used in aerobic digestion experiments to describe the rate of biogas production as a function of time for several organic substrates. However, the conversion of complex substrate containing different phases with dissimilar rate of degradation result in step curves that cannot be described by a single compared type model. For this reason, a multi-step version of the modified Gompertz model is proposed here to analyze the experimental data. So this is the equation of Gompertz type of model. And then we have the result of the research past before that for the biodegradation of bioplastic under aerobic condition in aqueous medium. This is the graphic that shows the result. So for the aerobic, the mineralization curve for the tested materials under aerobic condition after 117 days of testing, the degrees of mineralization of PHB, PHBF, and PCl were for PHB is 79.6 plus minus 0.4%, and for PHBF is 84.5 plus minus 9.3%, and for PCl is 75.7 plus minus 2.3% respectively. Note that considering the amount of dissolved inorganic carbon or DIC, the final biodegradation decrease, where for PHB is 83.0 plus minus 1.6%, and for PHBF is 87.4 plus minus 7.5%, and 77.6 plus minus 2.4% for PCl. This result will be considered as paste to be biodegradable according to the ISO standard pass and fail criteria as they reach at least 90% conversion into carbon dioxide, in comparison to the positive control within less than 3 months, or 90 days. So this is the result of the biodegradation of bioplastic under anaerobic condition in aqueous medium. You can see the graphic here, and what the result is the mineralization group based on the ratio between the net cumulative gas carbon produced, carbon dioxide and methane, and the theoretical amount of produced biogas are shown in the figure. Following 77 days of incubation, the biodegradability levels of PHB and PHBF on a gas carbon basis were, for PHB is 74.9 per plus minus 1.9%, and for PHBF 71.1 plus minus 2.4% respectively. However, when considering the amount of soluble inorganic carbon, or DIC, at the end of the test, the degree of biodegradation amount to be 83.9 plus minus 1.3%, and 81.2 plus minus 1.7%. So, influence of particle size, that after grinding and sieving the PBS in the resin form, the biodegradation of resulting sieve fraction, for example, 100 until 250, and then 250 until 500, and then 500 until 1000 micrometers, was evaluated under aerobic and anaerobic condition in aqueous medium. The specific surface area for the tested particle sizes was mathematically calculated by assuming the particle shape as spheres with a diameter equal to the median of each particle range. Two theoretical average specific surface areas were 274.3 and then 128.0 and then 64.0 centimeters square per gram. Material for the fraction of 100 until 250, and then 250 until 500, and 500 until 1000 micrometers respectively. You get less of the PBS, or biodegradation bioplastics. And this is there is a table that shows comparison of the model biodegradation kinetics for tested bioplastic at different particle sizes and conditions, aerobic and anaerobic. So for the notes is there are AE aerobic conditions, this one, and then AN for anaerobic conditions, and data on cumulative gas carbon productive from the different bioplastic were adjusted to the modified Gompertz model P carbon yield. So in this table, for the material that used is there is PHB, PHBF, and PHL, where this is the particle size range in micrometers, and then this is the days for the lag fast, and for R is the weight of gaseous carbon dioxide, and methane formation. This is, and for R square is the goodness of fed. Based on the obtained biodegradation results, small particle sizes are clearly advantageous to reduce the acid time for biodegradation to standard and to eliminate surface limiting effects in order to assess the intrinsic biodegradability of a material. So, the effect of the particle size on biodegradation kinetics is given in the table before. That kinetic data fitting resulted in calculated R square values higher than 0.985, indicating that the modified Gompertz model adequately described the biodegradation bioplastic or BBS biodegradation process. The cumulative mineralization rate was inversely correlated with the particle size regardless of the environment and bioplastic. The lower particle size herein tested supported up to 331 and 331 and 405% higher maximum aerobic and anaerobic biodegradation rates, respectively, than those obtained with a particle size of 500 until 1,000 micrometers. Particle size did not have a markedly influence at the lag phase among all the tested biodegradation bioplastics or BBS. Not that model slightly underestimated the lag time of the lower particle size, 100 until 250 micrometers under aerobic conditions. However, bioplastic biodegraded because less surface area was available for bacteria biodegradation. For instance, using particle sizes of 100 until 250, and then 250 until 500, and 500 until 1,000 micrometers, the anaerobic biodegradation of PHB and PHBF, which applied after 35 and then 42 and 65 days and 35 and 56 and 65 days respectively. Under aerobic conditions, the smallest particle size of PHAs required around 52 days of incubation to reach a plateau in the biodegradation, while the largest particle size needed a 3-month degradation time. Likewise, the aerobic biodegradation of PCl 100 until 250 micrometers started after 65 days of incubation, while 79 and 86 days were needed for particle size ranges of 250 until 500 and 500 until 1,000 micrometers respectively. So this is another research. You can see the table that showing the degradation rate of biodegradable plastic in soil and compost environments. There are the types of environment, soil, compost soil, and soil or compost soil that with the 90 and 10%, and for the compost and the plastic type, there are PBS, PHA, PLA, and there's a PCL and many more. And this is the degradation condition, the temperatures, humidity, and some pH. And this is the result of the biodegradability rates, and this is the duration this required to degrade. So of course that the result is there are many factors that affect and the natural environment of biodegradation are considered complex processes because many factors contribute to the degradation environment where biodegradation takes place, such as landfill site or a location within a landfill, freshwater or saltwater, and topsoil or deep soil. The rate of biodegradability for different bio-based plastic in different environment, including soil and composting, is illustrated in detail in table before. The degradation of biodegradable plastic is generally monitored by different methods, such as visual inspection, the spirometry system, such as biological oxygen demand or BOD, or carbon dioxide evaluation, physical procedures such as mass loss, biomass growth, and soil analysis. So we jump to the conclusion. The research before explored the biodegradation of various bioplastic under aerobic and anaerobic conditions, showing that PHB and PHBF biodegraded in all conditions, while PCl only under aerobic conditions. Carbon sinks were analyzed using C-balance, providing valuable insights. Although smaller particle size speed up degradation, this approach may not be feasible for waste treatment. Combining kinetic analysis with C-balance can improve biodegradable product design and waste management. The complexity of biodegradation in natural environments arises from factors like soil type, water conditions, and landfill characteristics, with rest monitored using methods such as respirometry, mass loss, and biomass growth. And then, so thank you so much for listening my presentation. I'm so sorry for my mistake. Ya. Wassalamualaikum warahmatullahi wabarakatuh.